watching The 9. The Michigan Science
Hi, everybody, and welcome to another episode of Echo Live. My name is Anna, and I'm coming to you from the Michigan Science Center's Echo Distance Learning Program. We've got a very exciting episode to kind of start wrapping up our week of making with an episode on coding. So today we'll be talking about coding, how we interact with computers, and how we give them instructions. So we've done a little bit of, let's see, why are we in the wrong one? There we are. So we've done a little bit of making this week. We've made some different robots and some different tinkering crafts like our cardboard automata and our doodling scribble bots that we made yesterday on Echo Live. But the problem with those two inventions or those two creations that we've made so far is that they can't necessarily work on their own. We can't necessarily give these inventions or these projects that we've done so far any sort of instructions. Our scribble bots were pretty cool because when we turn them on, they start to rotate around on our piece of paper. They doodle for us. But other than adjusting the hardware, the actual physical pieces of our scribble bots, like the orientation or the angles or the heights of our markers, or we could even use something besides markers like pens or pencils. But other than adjusting the hardware, we really don't have any way of telling these robots what to do. They're really just on or they're off. But we have all sorts of different robots in our daily lives that do receive information or instructions from the people who created them or the people who are using them. A couple of people already chiming in our chat feature. You see my good friend R2 is here. Now, we had a smaller version of R2, so little did you know that if you freeze an R2-D2 Lego in liquid nitrogen, they turn into a remote-controlled R2-D2, just like this one. I'm just kidding. They don't actually do that, but R2 is here to talk to us a little bit about how coding works. So what is coding, though? So my first question for you, if you're chiming in on any of our live platforms today, if you're on YouTube, Facebook, or here in Zoom, tell me in the chat feature, what really is coding? If you had to give coding a definition, what would you say coding is? So think about that. Tell me in the chat when you have an answer to what is coding. You had to give it maybe just a few words or a one-sentence description. So think about what we use code for. Think about if I wanted to use code, right? Oh, Zoe told me in Zoom that she knows that coding can be made up of ones and zeros. So maybe you're getting some context clues from my virtual background here. So coding can consist of ones and zeros. Elizabeth and Theo told me that it's a special series of numbers. So that special series of numbers, it means something, right? So it is special. A couple of people in Zoom have some definitions. Jason tells me that it's a program that tells robots what to do. An example would be something like binary. So if you're familiar with binary, which is the type of code you see behind me, that is made up of ones and zeros. And some great answers coming in. Like coding is the process of using a computer language to get a computer to behave the way you want it to. So we've got some seemingly coding experts out there. Lots of people naming me different types of code like JavaScript or Python. Great answers, everybody. So coding can exist in all sorts of forms, but basically code is a way for humans to communicate with computers or machines to tell them what to do. So our very first coding activity we'll do doesn't have anything to do with a computer language, but just to understand the basic premise or the purpose of coding, I would like to act as our robot today, and I'm going to have you code me how to make a peanut butter and jelly sandwich. So I've got all my hardware here. I'll be the robot in this case. And then I've got all the materials or supplies that we might need in order to make a peanut butter and jelly sandwich. Now think about your code. If you were to have to write this in a code for me, how would you get me started in this process? So think about all of the materials we have here. If I were to start making a peanut butter and jelly sandwich out of these supplies, what would be my first step? Go ahead and tell me in the chat. What is my first step to making a peanut butter and jelly sandwich? Ooh, okay. All right. Couples answers starting to come in. Jennifer tells me to open the jelly. All right, I can think of maybe even something even more basic than that. Someone told me to pick up the knife. Someone told me to open the jelly. Ooh. Put jelly on the bread. All right, but we have to think really basic with these instructions, right? We have to think the most basic we've ever thought, because computers are not people. Computers don't have any sort of background knowledge to work with when we're trying to do something like making a sandwich. Kathleen made a great point that I should wash my hands, and I did do that before the program today. Great thinking. Now, a couple people have suggested that unscrewing the lid to the jelly would be a great first step. So I'll agree. But even if I was a robot and I wanted to unscrew the jelly, you would have to get even more detailed, right? You might need to tell me to lift my hand, and you might even specifically need to tell me which hand am I supposed to lift, right? So I might need to lift my right hand, place it on the lid of the jar, hold the other side of the jar with my left hand, turn my hands to unscrew the lid, right? So even something that humans consider to be pretty basic, right, can be complicated when we're trying to communicate this to a machine. So then people are telling me now I need to lift the knife. And Priya tells me that I need to apply peanut butter to one and jelly to the other. But if I was a robot, right, I don't know how to do that. Honestly, what does apply the jelly mean, right? We need to think in terms of the steps I would need to take. This activity is supposed to be very difficult, right? Because things we take for granted become very difficult when we're trying to get computers or robots to do these things that are very easy for people to do. So your next step might be to use my right hand to get some jelly out of the jar. Transfer that jelly over to the bread. And then if we're going to apply it, right, maybe using a back and forth motion with my hand here in order to spread the jelly across our bread. So a back and forth motion, right? All of these steps don't come naturally to computers. Now, people have prior knowledge, right? So once we've completed our jelly side, people are now telling me put the lid back on our jelly jar, maybe set that off to the side. Then again, you'd need to tell a robot, right, how exactly to get to the next step. Maybe right hand on lid, left hand on jar, twist, set the jar lid down, pick back up our knife, scoop out some peanut butter, and then again, back and forth motion if we want to put the peanut butter on the other side of the bread. So coding can be very simple, just to understand the basic process, right? At this point, we might tell us to set the knife down, put the lid back on our peanut butter, and then finally, right, we need to sandwich our bread together. So this is just an example, right, of how coding works. We need to tell computers every single step, or robots every single step that they need to take in order to complete a task. They don't quite have the ability to guess what people want. But computers are getting smarter and smarter, right? But most of the time, computers don't speak English. We might be familiar with some sort of voice-to-text technology. So if you've ever spoken to Siri or Alexa or Google, right, we know that computers can recognize human language, but everything they do for us exists in the realm of code. So they don't speak English like you and I do. They don't speak in terms of words of do this or do that. Computers only speak in the terms of on and off. The most basic type of code would be binary code, which is represented like these numbers behind me. Binary code is all ones and zeros. Ones and zeros represent ons and offs in terms of computer language. So we have a binary code kind of decoder over here on the left of the screen. And this is the capital binary alphabet represented in terms of ons, which are ones, and offs, which are zeros. Generally, when we speak in binary, we work in terms of bits. Or if you've ever heard of something that is 8-bit, this is what we're talking about. So each digit or each place in one of these letters is a bit. So this list is in terms of an 8-bit code. There are 8 digits to represent each of the letters up here on the screen. Again, ones are ons and zeros are offs. Now, computers, we don't really type things out like words, but this is a good way to start understanding that if we were to write something in code, these codes can get extremely long, extremely quickly, almost looking like my background after just a little bit of time. So I'd like if we could practice decoding or encoding some binary alphabet letters. So I've written the initials to the Michigan Science Center up here. So we'll start by just trying to write the code for these 3 letters, for M, S, C. So what we'll need to do is find the corresponding letter over here on our board. Let me get my drawing tool out. So we'll need to find the corresponding letter. So we want the M, which we see right here. We want the S, which we see right here. And we want the C, which we see right here. So go ahead and practice writing or encoding using this binary alphabet. Try to type out these initials in the correct order, right? Because order of operations is extremely important when we're talking to computers. They don't have the same logic as people where if you make a typo, they might be able to rearrange or figure something out. They only know everything in exact. So you need to be exact, but go ahead and practice typing MSC using this 8-bit binary alphabet. It works almost like a secret code. Go ahead, type it in the chat when you've got it. Give you a moment to work on that. Lots of answers starting to come in. You guys are doing awesome. It's a little tricky, right? So this isn't exactly how we communicate with computers because like we said, we're not trying to write them messages in English, but each one of these digits might represent an on or an off switch in a computer or a robot that commands a task or a motor or a test for the computer to run. So these are all really, really important. And this is great practice. So lots of good answers coming in. Let's go ahead and we'll try typing this out together. So if we're looking for the M, right, we can see that according to our binary table there, M is represented as 0, 1, 0, 0, 1, 1, 0, 1. So that's M. Next letters would be S. So 0, 1, 0, 1, 0, 0, 1, 1. And then for the C, our very last letter, 0, 1, 0, 0, 0, 0, 1, 1. All right. So it's pretty simple, right? Pretty simple stuff. All we need to do is look to our binary code table and then translate that into text. But we can also do this the opposite way. We can also do this in reverse. So I'll go ahead and clear that. Let's go ahead and take a look at our next slide. So we can also write messages in binary code that need to be translated back in to alphabetical letters. So I have a message here on our sticker, a little bit of a clue up top, but go ahead and we'll put that table back up next to our name tag here and tell me, what does this say? So go ahead, use the table, try to look at those sequences of numbers which are on and off switches, and can you tell me what this message says? So this time we're not looking for the ones and the zeros. This time we're looking for the letters that they represent from over here on our binary alphabet table. So I'll give you a moment to work on that. You guys are doing awesome. Some people starting to work through this. Good job, everybody. Maybe a little bit too big of a hint. Maybe I should have gone with something a little bit more challenging because you guys are so smart. But let's go ahead and let's look for this first. Let's go ahead and look for this first sequence. So this is 8 letters right here, or 8, I'm sorry, this is 8 bits right here, which represents 1 letter. So we're looking for 0, 1, 0, 0, 0, 0, 0, 1. And that one might have been kind of easy to find because it is A. So we know that our first letter is an A. The next letter, we have 0, 1, 0, 0, 1, 1, 1, 0. So it might take you some time to kind of pan through these lists here. Binary definitely has a lot of combinations. So if we look through, you can see that the second one is an N. So we've got A, N, and then the next one is 0, 1, 0, 0, 1, 1, 1, 0. And if that sounds familiar, it's because it's the exact same as the last one. So we've got another N, and then our last 8 bits are the same as our first 8 bits, which was another A. And so this message says, hello, my name is Anna. So that is my full name in capital letters represented by binary code, which is pretty cool. But, right, we can't always, a lot of other people have longer names than I do. And so it might take you a little while to write a full message in binary code. And we don't necessarily have everything we might need to write full messages here. But binary code does not just cover the capital alphabet. So there are 26 different sequences of numbers here, but we're not limited to just 26. You might be thinking to yourself, well, what if I wanted to use lowercase letters? Well, we can just use more 8-bit code, right? So as our table gets more and more combinations, we can add even more letters or symbols to this sequence here. Now, we can have either a 1 or a 0 for every single digit, which means that the total amount of possible combinations of an 8-bit code, where we're only using 8 different digits, or 8 digits total represented as ones and zeros, is 2 to the 8th power. So 2 times 2 times 2 times 2 times 2. I might have ran out of 2s there. But total, that gives us 256 total combinations. So even if your name might not be represented by these letters, say someone like R2D2 here, he's got numbers in his name. Or maybe if your name is something kind of crazy like Elon Musk's child's name, not quite sure how you'd pronounce that or how you'd say it, but they would definitely need some different sorts of symbols or characters, which can still be outlined by binary code. It's just not written here on this alphabetical table for us. All right, so let's take a look at our next activity here. And this is something that you could recreate at home pretty easily. Got my comments up there so I could monitor. But what we'll be doing is creating some binary bracelets that you can use to write your own name or your own secret message using our binary code table here. Zoom out just a little bit. So we've got our binary alphabet yet again. Scoot my sandwich making stuff off to the side. We've got our binary alphabet here. And then what we can do is represent our code in terms of ons and offs using 2 different colored beads. And so you can actually make yourself a wearable piece of binary code. So we will do the initials of the Michigan Science Center. Really, you can't do too long of codes unless you choose some smaller beads, but we're just going to string them onto our pipe cleaner here in the order of their codes, representing ones as reds. So red represents a 1, and blue represents a 0 or an off. So ons and offs, or ones and zeros, reds and blues. So let's go ahead. If you can tell me the digits for an M, go ahead and tell me the digits for an M using our binary code table here. Will you type those in the chat for me for just our first letter, which is M? We'll do them one at a time all together here. We're looking for an M, and we can see that all of our letters start the same way because we said there's 256 total combinations. So all of these ones begin with the same 2, which is 0, 1, and then we've got lots of people telling me in the chat, 0, oh, nope, wrong one, almost did it wrong, 0, 0, 1, 1, 0, 1. All right, so we've got M. Next letter is S. So I'm ready for us to tell me in the chat, what is the next sequence of bits, or my next 8 bits, if we're looking for a capital letter S? We know that it starts with, of course, oops, my scribble bots went down, 0, 1, 0, 1. Lots of people telling me in the chat. Good job, everybody. 0, 0, 1, 1. So 2 reds to end out S. We've got M for Michigan, S for science, and now our very last 8 bits is for C, for center. So go ahead and type that one for me in the chat. We've got 0, 1. Just do this, 1. 0, 0, 0, 0, wait, 1, 0. Good job, everybody. So this is a really easy way to practice your binary code. All you really need to practice writing in binary code is 2 different objects. So something to represent ons and something to represent offs, or ones and zeros. So this we can then just very easily twist around, turn it into a bracelet, and then I can take it with me everywhere I go and talk to people about binary code. So super duper fun piece of wearable technology. But what if you don't have beads at home? That is okay, because you can really use anything to represent ones and zeros. All you need is just 2 different types of objects. People have done this with, you can represent it as different colored squares if you're writing it. So you can either color squares in or not if you want to represent ones or zeros. So in this case, the ones are these, the ons are these white squares, and the offs are the black squares. But you can also do this with something kind of fun like peas and carrots. So while you're eating dinner, you can still be practicing your binary code using your vegetables. So in this case, right, our ones are carrots and our zeros are peas. You can also do it using things that aren't necessarily different. So in this one, someone is representing their binary code with goldfish, but ons are goldfish that are pointed up and offs are goldfish that are pointed down. So even if you only have one type of object or one type of snack with you, you can still practice your binary code wherever you go. Our very last activity that we're going to talk about here on our Coding Unplugged episode of Echo Live is coding a dance party. You might have been wondering, why do I have my disco ball here in the studio? But we will be having a coding dance party. But first, you'll need to figure out exactly which kind of dance moves or which type of dance I'm trying to code. So I've got another series of codes here, or another series of instructions that I would give to my dancer or my robot if I wanted them to follow along in this dance. I'll show them to you and tell me in the chat or in the comments, what dance are we coding with these 4 images. So a very, very simple dance, one most people have heard of before, represented by only 4 main steps. So in our first step, we see that we need to open and close our hand 4 times. All right, so open and close your hand 4 times. The next one shows us that we need to put our elbows out to the side and then wiggle them up and down 4 times. Step number 3 tells us that we need to swing back and forth or shake our hips 4 times. And then lastly, we need to clap our hands 4 times as well. So if you know what dance we are trying to code using these 4 basic steps, go ahead and tell me in the chat. What dance do you think this could possibly be? Awesome job, you guys. This is, in fact, the chicken dance. So we've got the chicken dance here coded in these 4 basic steps. So all we need is just open and close your hands 4 times. So 1, 2, 3, 4. Next step, right? Shake your swing your wings up and down 4 times. 1, 2, 3, 4. Then shake your tail feather 4 times. 1, 2, 3, 4. And clap your hands 4 times as well. 1, 2, 3, 4. To celebrate the end of this episode, I think it'd be awesome if we had a coding dance party all together. Now that we all know the steps to the chicken dance, everybody can follow along, but it wouldn't be such a dance party here if I didn't have some help from some fellow STEMinistas and some fellow MySci and Echo Live staff members. So we've got some friends who are going to join us here on the Zoom call. So come on in, everybody. Get ready for our chicken dance party. Hi, everybody. Look how cool. We've got everyone joining us here from Echo Live. We've got Raul and Paulette, who we've met before. We've got some fellow STEMinistas and STEMinista family hanging out. We've got MySci staff. Oh, yeah. Showing off our MySci swag here. All right, so we are going to go ahead. If you'd like to follow along, remember, all you need are those 4 basic steps with our hands, our wings, our tail feathers, and then clap your hands. So here we go with our chicken dance coding dance party. Thank you, everybody, so much for joining us. We hope you followed along at home, so we weren't the only ones just messing around being silly here. But coding can be that simple, and it can be that much fun. Even R2D2 was getting jiggy with it here to our coding dance party.
So with that, it brings us just about to the end of our show today. If you are interested in seeing more Echo Live, we will be back tomorrow at 2:30 p.m. These programs are free and they take place every single weekday. If you are looking for at-home science activities that you can try, visit our website. It's listed right here on the bottom of the slide. You can find some at-home science activities for you to try at home. Think about coding, think about making. All of the activities that we've done so far this week are listed on our website. So thank you everyone so much for joining us. We hope we'll see you back here tomorrow and have a great rest of your day. Bye everybody, and thanks everyone so much.